Hello. Today what I'm going to do is talk about analog sensors for measuring position or measuring motion, and particularly displacement today. And so displacement, distance, proximity, gap, etc. are the things we're going to be talking about. We're going to talk about some different technologies for measuring these things. We'll eventually talk about velocity and acceleration, and we'll mention jerk. And you ask what's jerk, and me most of the time, but jerk is the higher order derivative. So you've got acceleration as being the second derivative, and then you have higher order derivatives. And all of these higher order derivatives are grouped in what's called jerk. Turns out that our inner ears are quite sensitive to jerk. Elevator manufacturers go to a great deal of effort to limit the amount of jerk in an elevator. That's why you'll see an elevator car slow dramatically right before it gets to the floor, and then it will slowly approach the actual floor it's going to or actual position it's going to stop. And the reason they do this is so that it won't jerk. I heard a story about a roller coaster manufacturer who the profile of their roller coaster was such that it was creating incredible levels of jerk for the passengers, and most of the test passengers would get off the roller coaster with blood coming out of their ears. And so they had to kind of modify the profile in order to take care of that. One of the simplest displacement measurement devices is a simple potentiometer. These can be placed in a voltage excitation circuit in a voltage divider arrangement, and the total resistance of the potentiometer is R, and this consists of a high and a low value, and I can figure out what the low value or what the voltage out is using a voltage divider equation. Noticing on the bottom here that this is just R. I end up with an equation that describes the output voltage. And I would love to get this into a form that's V out is some proportionality constant times X. Well, it turns out that if the potentiometer is linearly wound, as it's called, that position that I'm at will be proportional either to the X linear displacement or to the rotary displacement. If it's a rotating pot, you can buy slide pots that will be linear. And I get R low is equal to some K0 times X. And I can substitute that in, and I end up with this being the proportionality constant times X, and I get it into the form that I wanted. And that says that V out is linearly proportional to X. Now, there are two things you're going to notice. One is that in my constant, I have V excitation and I have R. That means that for this output voltage to be consistent for the same position, I've got to have the excitation be a constant. If it changes, X will change. I've got to have R be a constant. If it changes, R will change. So I either have to make an effort to make sure the excitation voltage is maintained at a constant enough value so that it doesn't change, or I have to change. I have to make sure that R stays the same. Now, two things change excitation voltage. Like if I were doing this in a battery application, the battery voltage, the battery's discharged, the voltage drops, my X positions would all change, and that wouldn't be good. So I have to either ensure that V excitation stays the same, or I have to take into account the variations due to V excitations. One of the things I can do to this equation is simply divide it by V excitation, and this creates what's called a ratiometric output. And ratiometric outputs allow me to maintain the same X value, same voltage value per X for any value of excitation voltage. Second thing is R changes. What would cause R to change? Well, temperature. And so I have to be careful about something called self-heating. I have to make sure that the current that I'm driving through this loop does not cause the resistor to heat up significantly and thereby change the resistance. Okay, so the output voltage is linear with respect to position, and but I have to measure this with some device. And so this measurement resistance is called input resistance of my measuring device. I'm calling it our meter. And so I've actually placed these two resistors in parallel, which changes their value and which changes the linearity of the device. And so and just qualitatively, what I'm going to have to do is keep our meter high. You can kind of see that in these equations if you go through them. As long as I keep our meter high enough, I won't have a great effect. Now, how much of an effect will it have? Here's a graph of this. The straight line here is our meter is essentially infinite. This is our meter is our meter divided by the low value is 10. This is, it sags more when they're equal, and sags even more when our meter is substantially smaller than the low resistance. And what do? I have to keep our meter higher. And what if you can't do this? You may have to go to some sort of linearization method in order to fix the problem. One of the things I have to be concerned about if I'm using a microcontroller and I'm using the A to D converter, the A to D converter on typical microcontrollers may have an input impedance of only 1 kilo ohm. That means if I happen to buy a 10K pot, a 10 kilo ohm pot, that I'm right there with that curve. And I'm going to be confused for at least a day trying to figure out why I'm not getting a linear value out of the device. And it's due to this phenomenon. Okay, what are some pros and cons of using potentiometers? They're cheap. You can buy them for dollars and sometimes sub-dollars. They're cheap. They're simple to interface. Obviously, you just have to excite it and read the voltage. And plastic potentiometers, they have a plastic conductive surface. They have really good resolution. And so, it's essentially infinite. Now, the cons of potentiometers, it's a mechanical contact. They are rubbing, and so they will eventually wear out. And in particular, they're going to wear out if they're moving really fast. It's a bearing surface, and it just will wear out. They're sensitive to excitation, as we talked about. Wire wounds only have a fair resolution due to the fact that a wire wound resistor is just a series of coiled wires with a bare strip down the center of them, and the wiper arm runs back and forth along these, and so the little wires tend to create a lot of electrical noise. They also heat up. Two reasons they heat up: electrical self-heating and mechanical heat, because they're being run faster than they can stand. And so that's a con, and that will cause wear to happen very fast. Another family of position sensors or variable inductance sensors, there's what's called LVDT and RVDT. This stands for linear variable differential transformer. People will tell you it stands for other things. It doesn't. And so you can, these are a very typical sensor. However, they are pricey. You're going to be $250 to $400 for one of these. Now, they consist of a primary coil and two secondary coils. And what happens is I excite the primary with an AC voltage. The reason I have to use an AC voltage is because this is a transformer, and it will not transform DC. And what I'll get out of this as the core moves up and down is a modulated amplitude. So the amplitude will go up or down depending on where the core is, and the phase also changes, but I'm going to get an output that varies in proportion to the X position. You'll notice this is also likely sensitive to excitation voltage. It is, and so what I can do is take the output voltage that's produced and divide it by the excitation voltage to get a constant ratio. Now, since this is a modulated DC or AC signal, it requires a demodulator to work with. Analog Devices makes a nice one that's all on one chip, and it works very well. And so if you're going to use those, you might consider using these. The rotary version of this is called a rotary variable differential transformer, and it measures angles. What are some pros and cons of RVDTs and LVDTs? They're very accurate, and they theoretically have infinite resolution. It's an established technology. They're non-contact. The little core never has to touch anything that the windings are wound around, and they're small or smallish. They can be durable if they're properly handled and installed, but they have very fine leads, and those very fine leads can break. I ran into one of my technicians when I was at my first job twirling an LVDT by its leads in the lab, and we had a discussion that day. And so it's again, they're expensive. You're going to pay money for these, plus it requires the demodulator, which you're going to pay more money for. What else could we do with inductance? We can sense proximity. So we have some arrangement like this in a ferromagnetic target. As we get closer and closer, inductance is going to change, and I'm going to be able to sense that and make some decision from that. There's also self-inductance, where I just have a single coil with a core, and as the core moves in and out, the inductance will change, and as that inductance changes, I can sense that and use that. My first mentor produced a sensor called FastR, which was a single inductor. He had a very clever spiral winding on the outside of this coil that did amazing things, and he would never tell me what it was. And I don't resent him for it, but it was like, what does it do? And he would never tell me. This is also eddy current sensors. Eddy current sensors, I have some core with a wound coil on it, and the closer I get it into a target, a low resistivity target, I induce currents in the target, and that increases the inductance, and the more it increases the inductance, I can sense how far away I am from the target. Now, as I say here, typically this sort of transducer is conditioned, and that read is made useful by placing the device in an impedance bridge. Remarkably, mechanicals are more likely to have seen these than electricals. This impedance bridge, I've got some RF source, and it produces a modulated signal just like a LVDT or RVDT. When it's balanced, it reduces to this, and my output voltage goes to 0. Okay, this is some general equations for the impedance bridge and showing when it's balanced. When it's balanced, the imaginary parts will go to 0, and the conditions for which that will occur are the trivial example of omega equals 0, and this condition that's shown here. So that's when the system will balance, and then I will get 0 output, and then I can detect small changes in inductance in one of the legs, and that will tell me, give me the information I need. Capacitance is usually small, and for small displacements, and particularly if you're using air as a dielectric. One of the interesting applications is measuring liquid levels in tanks. If the fluid has a relative dielectric constant that's much greater than air, as the fluid rises up, the capacitance will change in this equivalent circuit down here. And I can detect something like this using a capacitance bridge with an op-amp in here. And the bridge will be balanced under certain conditions and not under, and I can get a proportional voltage out that tells me the depth of the fluid. Okay, capacitive displacement sensors. If I have a fixed plate and a movable plate and I move the plate in and out, this is similar to the capacitive microphone that we talked about. Turns out that capacitance change is inversely proportional to X, but by conditioning the capacitor, I can, or conditioning using an op-amp, I can get it so that the output voltage is proportional to X, and then I can use it as a gap sensor. Or now again, these are usually for very small gaps. They don't work well when you get far away. Okay, I can also have rotation sensing. So I have a rotating plate and a fixed plate. And so basically what happens is I will rotate off the center, and so my overlap area will change, and that changes the capacitance. In this case, capacitance is proportional to the angle I've rotated, and the sensor responds linearly to theta. And so I can condition that easily. Capacitive sensing also, I can sense an over plates, the same thing. Overlap, I change the overlap, I change the spacing, and I get a change the overlapped area by sliding this plate back and forth. I can get a measurement of position. There's lots of other ways and lots of other sensors. We'll go over some things like velocity sensors and velocity and acceleration, and jerk I'm going to ignore, but and then we will do digital sensors like encoders and stuff like that. So I'll post this up and then post a discussion if you've got questions about it. If you've got questions about sensing for your projects or anything like that, please talk to me about it. And all my best to you, and we'll talk to you later. Bye.